Bismillahirrahmanirrahim. This is lecture number 19. In our previous lecture we have calculated equation of motion for displacement. Then we have supposed its solution, and then we have defined a tensor known as propagation tensor, which is a second order tensor, and that has obviously 9 components, and we have shown that this tensor is symmetric. Let's see something about the eigenvalues. It's as gamma is real. We have seen that gamma is real tensor and symmetric tensor. So principal values, that are eigenvalues, will be real, and principal directions are orthogonal. This is a theorem. Principal values are real and principal directions are orthogonal for a real symmetric tensor. So let's see that any further condition on the eigenvalue. What are the eigenvalues? These are the eigenvalues of v square. P is the principal direction for matrix of this tensor, and rho v square are the corresponding eigenvalues of this tensor, of the matrix of this tensor. And we now start. We know that gamma IL PL equals to rho v square PI. As we want to look something on eigenvalues which are rho v square, so we will try to write this eigenvalue explicitly in the form of this gamma and principal directions. So what we do, we operate with pi on both sides. When we operate pi on both sides, this is left side of this from this side, and this is right, and we know that as p is unit vector, so if you will open the summation on I, then you will have p1 square plus p2 square plus p3 square, and this should be equal to 1, and this will be equal to 1. Why it is 1? Because our p is unit vector, so it must be equal to 1. So here it will be rho v square, and on right hand side we have gamma IL PL PI. And we know that gamma IL equals to Ci JKL Nj Nk. We can write this in this way by rearranging the factors. We can write Pi Nj, Ci JKL, PL and Nk. Now let us take P equals to this. Any tensor Aij, Cijkl, Akl. This is any product of three quantities. This is fourth order, this is second, and this is second. And we know that, if you remember, that any tensor can be decomposed its symmetric and anti-symmetric part, and we can write components of that tensor in this form. This plus is notation for symmetric part, and this bar is notation for anti-symmetric part. So this is the symmetric part of this and this is the antisymmetric part of this, and this is tensor itself equal to sum of symmetric and antisymmetric part. So this is in this way we can decompose any tensor. This symmetric part is equal to aij plus aji divided by 2, and this is equal to aij minus aji divided by 2, if you remember. Similarly, we can write this. This is symmetric part and this is antisymmetric part. Now we have used this decomposition. Keep in mind that this decomposition is always unique. It means that if you have if you are asked to find to decompose this matrix, then this result would be unique for a tensor. Obviously, when you change the tensor, obviously it will be changed. Now, using these decompositions in this equation, we have this aij plus and this. Now multiply all this and we have these 4 components, and we know that aij bar equals to minus aji bar, because this is antisymmetric. This is antisymmetric part. Similarly this, so we can write a bar ij cij kl as interchange j and I with each other. We have this thing, and then putting the value of this here, minus aj, and this is symmetric. You know that this is symmetric in pair, so it would be minus a bar ij cij kl. So when you will take this on left hand side, you will have this a bar cij kl equal to 0. This thing is equal to 0. It means this term is equal to 0. This term is 0. Well, let's see what happens with this. Similarly, this is also 0. You need to do similar steps as we have done here. Then you will have this thing, this product of 2 equals to 0. So when you use these zeros here in this equation, we have this p aij plus cij kl a plus kl. What does this mean? That we are left with only symmetric part of a on both sides. This is symmetric part, this is also symmetric part. And as we know that C is positive definite, if you remember that C is positive definite, then for any x where you have written x transpose ax must be greater than 0 for a positive definite. As C is positive definite, that there you have written S transpose strain S transpose C S greater than equal to greater than 0, because C is positive definite. From where that thing has come, there you have used strain energy function, and you have said there that W is greater than 0. Strain energy function is always positive, so W is greater than 0. So when W is greater than 0, S transpose C S greater than 0, so C is positive definite. So for the definition of positive definite, if matrix A is positive definite, if X transpose AX greater than 0, as C is positive definite, so this must be greater than 0. When this must be greater than 0, P is greater than 0. So, and what is P? P is this. Initially P is this. After using your result of decomposition, you have seen that P is equal to this. When P is equal to 0, let us take aij equals to nipj. So when we take nipj, then we have seen that here would be AIN PINJ CIJKL PLNK. This is AIJ, this is ALK, AKL, AKL. You can write ALK because this is symmetry. Because at the end you have a symmetric result. But we are writing with the same, that PINJ PK PLNK. So you can write NK PL. So here we have written AIJ CIJKL AKL because sorry, I have said that this thing is symmetric. A is not symmetric basically. After simplification we have left with only symmetric part of this A. So you have to write this P in this fashion, AIJ KL then AKL, because you can see that IJ KL KL. Okay. Your IJ will be PINJ and your AKL will be PLNK. It is, and this is, and there's nothing wrong if you write AKL equals to NKPL, because these are simple components. These are simple components. A1 2, if K is 1, L is 2, then it would be P2 and 1. You can write P2 N1 equals to N1 P2, nothing will happen. So either you write N here, P here, nothing will be wrong. But AIJ equals to this and AKL equals to this. Don't change, don't write it ALK. It would be AKL. This thing is positive, so if take NIPJ, so it would be NIPJ and this would be NKPL. This would be greater than 0 and this is equal to rho v square, rho v. So here we have seen that all eigenvalues are positive. So it means that when you have propagation tensor gamma, then eigenvalues would be positive, real and positive, and corresponding corresponding directions will be, direction means corresponding eigenvectors, corresponding polarization vector, principal direction, they are orthogonal with each other. We have seen this thing here because it is real and symmetric. So principal directions are orthogonal, and we know that all the eigenvectors of this tensor gamma of the matrix corresponding to this tensor are unit eigenvectors, and we are calling those vectors as polarization vectors. So by finding the eigenvectors of this of the matrix of this tensor, we mean that we will have polarization vector. And with the help of these two things, these two vectors, which vectors? One is propagation vector, which is denoted by small n, small letter n, and second one is polarization vector, which is p. And with the help of these two, we will define our longitudinal wave and transverse wave. Now we will see that how many waves are there in a material. There will be 3 waves propagating in the same direction. Why we are taking same direction? Because n will be fixed. And why we are saying 3? Because there will be 3 principal directions. There will be 3 principal directions which are mutually orthogonal. This is written. There are 3 waves propagating in same direction with mutually orthogonal polarization. Polarization means mutually orthogonal principal directions, eigenvectors. So it means that we will have 3 pair, and with the help of these 3 pair we will define our waves. N is fixed, first polarization vector, second and third, and these polarization vectors will come as you calculate the eigenvectors in your previous classes with the help of eigenvalues. First you find the eigenvalues of the matrix, then by using those eigenvalues we find the eigenvectors. So in similar fashion you will find the polarization vectors, which are basically eigenvectors of the matrix corresponding to tensor gamma. So we have 3. Suppose that if one of them is longitudinal wave, then what does that mean? That for longitudinal wave we mean that polarization and propagation are in same direction. NEP will be equal to n, parallel to n. Then other 2 will be transverse wave. How they are transverse? Suppose that wave corresponding to this pair is longitudinal, that is P1 and n are perpendicular. No, we have to show that other 2 are transverse. How they can be shown? It can be shown because we know that P2 and P3 must be perpendicular P1. P2 and P3 must be perpendicular to P1 because we know that all the orthogonal polarization are orthogonal with each other. So when these are perpendicular to this P1, so automatically they will be perpendicular to n because n and P1 are parallel with each other. So when these are perpendicular to n, so we will have transverse wave by the definition of transverse wave. So if none of them is longitudinal or transverse, that means that if we have no longitudinal, no transverse wave, then which type of wave will propagate? So for that purpose we will have to find the angle between n and P1, n and P2 and n and P3. Then that angle will tell us that which type of wave is propagating in that particular material. The wave with smallest angle is called quasi-longitudinal. Why it would be quasi-longitudinal? This is what is used for differentiate from longitudinal wave, because we know that if n is exactly parallel to P1, then it will be longitudinal. And when the angle is very small between n and polarization vector, propagation and polarization vector, then it means that it will be close to longitudinal, and we say that quasi-longitudinal. And if the angle is near to pi by 2, then it means that we have quasi-transverse. Simply because we know that angle between n and p is, if angle between n and p is pi by 2, then we have transverse, and then if it is close to pi by 2, then it would be quasi transverse. So this is the case when we have no longitudinal and no transverse. So it means that we can have quasi longitudinal and quasi transverse in this case. Now we will find the components of gamma, this tensor. It would have 9 components, you know that. We will write here simply the explicit form of these components. We can write by open the summation on j and k, this right hand side. Now if 1 1, when I and L 1 1, then we have on right hand side simple this, then when after opening we have this. This is gamma 1 1, this is the result of gamma 1 1. C 1 1 and 1 square, C 6 6, C 5 5, 2 times and 2 times. Again gamma 2 2, we will have this type of result, gamma 3 3, and this would be gamma 1 2. This is gamma 1 2. So no need to find gamma 2 1, because we know that this is symmetric. So it will have 6 independent components, and with the help of that 6 you can write other 3 components. Diagonal will remain the same, and you will write the off diagonal components with the help of symmetry. This and this. This is gamma 1 3. This is gamma 2 3. These are the 6 independent components of gamma. For where n is polarization vector, propagation vector. N is propagation vector, and C's are the components of elasticity matrix. So it means that components of gamma will depend on the components of elasticity matrix and polarization propagation vector n. Obviously n1 square plus n2 square plus n3 square is equal to 1, because this is unit vector. So this is the today lecture, and for in the next lecture we will discuss with the help of this tensor that which type of wave will produce in the materials, like such as for monoclinic, orthotropic, trigonal, tetragonal, hexagonal. Then after that we will discuss isotropic material, that which type of wave will propagate in an isotropic material. How we will do that, we will see this thing in the next lecture, coming lecture, inshallah. Thank you so much.